When this is implemented really well, this is going to be great. And this is the neighborhood collectives. This is another feature that was added in MPI 3. So the topologies that Rajiv just talked about just describe sort of an interrelationship between the processes. It doesn't do any communication. Similarly, collective communication describes communication among all these processes, but it doesn't have any specific pattern. And so neighborhood collectives are a way to sort of marry the topology description, which is a nice way of saying which processes talk to which other processes, with the collectives, which is a nice way of communicating to the MPI implementation, as well as to a programmer reading the code, that here's a place where everybody is doing some communicating, but not necessarily with everybody else. So for example, you could set up a neighbor exchange, just like we've been doing, where you communicate with neighbors plus and minus 1 in each of the coordinate directions. And you can define the buffers that are sent and received to be laid out in the same sort of neighbor sequence. So you could set up a Cartesian topology for your processes, use this to connect them together, use MPI proc null to say it's not periodic, it's just throw the data off the edge. As an example, you could use an all gather to gather data from every, gather your neighbor data from all of your surrounding neighbors. So it's an all, but for the neighborhood collectives, all just means those processes in the topology as opposed to all the processes in the communicator. You can also do this with graphs. And of course, you want to use the disk graph, not the regular graph. The nice thing about a disk graph is fairly complicated and it's got all of those different changes, but it's got in and out edges, so you can define quite general patterns. Interestingly enough, many years ago when machines were much smaller, on one machine, it turned out that one of the fastest ways to do a halo exchange was to do an all-to-all V, where you used a V with lots of zeros in it to say that you only communicated with a handful of neighbors. Why was this so fast? Well, one of the reasons it was so fast was that the implementation knew that because it was an all-to-all, it knew that everyone was communicating. And it used underneath it used one-sided operations to move the data. And it could do that because it knew it was a collective operation. That made sense when you only had 1,000, because 1,000 zeros, in fact, running through that, looking for the non-zeros, was quick enough that the overhead of that was smaller than the benefit that you got from the fact that you could do this collective data move. Now with machines with hundreds of thousands to millions of processes, that overhead is much too large. But with these neighborhood collectives, you get both advantages. You get a compact description of the neighbors. And now you don't have to look at a bunch of zeros. You just have the neighbors. But you still know that it's a collective operation, that all the processes are contributing, which means that instead of sort of send-receive, where in send-receive you don't have any promises about the destination process having done the receive, so there's a limit to the things that you can do to optimize these patterns. Here the implementation can optimize them. So that's the hope. Current implementations, as far as I know, are functional, which means you can write the code. I don't believe any of them yet provide the sort of benefits that we're expecting to see. But again, I think that will come about in the next couple of years. At the same time, these are nice ways to write the codes. And as we'll see, okay, so here's like neighbor all-gather looks pretty much like an all-gather, except that instead of size of communicator data messages, you get in-degree data messages that are received, and it sends out degree messages. Then there are the non-blocking versions. So these non-blocking versions also give you a way to write a non-blocking halo exchange where you can do the halo exchange, do your computation, take advantage of communication computation overlap, and then do a wait on the single request as opposed to a collection of requests that you might have to manage. So sort of summary for these two things. There are these topology functions in MPI. They provide a way to give information to the implementation. In a few cases, current implementations take advantage of that information, particularly on the blue jeans. There's also been some good research work. It's also a good way to organize thinking about the topology, even if what it means is you do the implementation. So, for example, the idea in MPI is that you describe a topology and get back a communicator that you use, and that a communicator that has that topology. Well, if the MPI implementation doesn't do a good enough job of giving you back the right communicator and topology, then you should do the same thing in the sense of you should figure out how to get back the right communicator that's ordered the way you need it. You can use attributes to provide the other data that you might need on that communicator, and then communicate with it. And if you run into an MPI implementation that does a great job, maybe a better job, setting up the process topology, then you just use that communicator. Your code doesn't even have to change, other than you ripping some code out, which is always a gratifying experience. The other thing to bear in mind is the impact of the topology is really real. SMP nodes make it even more critical that you have a realistic abstract machine model when you think about the performance you're expecting to get, and that you understand the kind of performance and the different places where you have bottlenecks in your system, and organize your algorithms in code to deal with that. So maybe one of the most frightening things I have said today is that MPI everywhere model, which has all sorts of things to recommend it, has some serious and eventually fatal flaws in terms of the way in which it can share the communication resources. So that means that the codes really have to start being re-engineered to reflect the fact that you have these SMP nodes. You cannot just pretend that a SMP node is a bunch of isolated cores that are adequately provisioned with enough performance to be thought of as completely independent. You just can't do that anymore. Okay, and it doesn't matter whether you're on a Blue Gene or a Cray or an Intel processor. You're just not going to be able to do that, and it's just going to get worse with time. We also have these neighborhood collectives, which give you a nice way to express these sort of collective communication patterns. In particular, the non-blocking ones allow you to express what would otherwise be a bulk synchronous programming model, but by making them non-blocking, you can weaken the synchronous enough to give the MPI implementation and the hardware enough time to shuffle all the data around. By having that sort of collective description, you potentially provide, well, you do provide the implementation with enough information to do a good job in that communication. We hope and expect that over the next couple of years, implementations will take better advantage of that so that you won't have to essentially roll those out of the individual pieces. Okay, so that's why it says potential here. Right? So I think these are good things, but the reality is that right now, you probably won't see any benefit over using individual send receive, well, individual I sends, I receives.